In lesson 81, we're going to look at our second type of solids of revolution, so part two, and we're going to look at this idea of washers. Um, in previous lessons, we've looked at the area bound by one curve and rotated around an x-axis to get a solid, and now we're going to look at actually rotating two curves. So let's jump over to this computer program to take a look at this. Once again, we're going to be looking at some solids of revolution. And in this case, what we have here is 7 times the sine of x over 3. And so we'll just look at this real quickly. Remember, we revolved this. We're going to revolve this around the x-axis. And so it looks like this. You can kind of watch it revolve. And we have this whole thing and all these different shapes here. And this is a solid of revolution. And what I'm going to do is I'm going to limit this, and since the period here is going to be 6 pi, let's just look at from 0 to, so the whole period is 6 pi. Let's just go for this half a period, so from 0 to 3 pi, which is about 9.42. And we'll set that. There's the function. We can revolve it one more time. We can see it. We can see this shape coming. There it is. And we know how to find the volume of that. We can integrate between 0 and 3 pi. And we would do pi times the function squared. So 7 times the sine of x over 3 squared dx, and that would give us the volume of this thing. Now what I'm going to do, we also obviously could do the same thing for, let's do 5. So I'm going to reset it. Notice I'm changing the amplitude to 5, so it's not going to be quite as high. We could revolve this around the x-axis, and we get this shape. So similar shape, just smaller. And so there we could find the volume of that. Now what we want to do is we're going to do something we did similarly with when we looked at area under a graph or area between two graphs. We had to take one minus the other. So if we think about this, if we think about, let's have this one with the 7, and then let's have the same function, so 5 times sine of x over 3, not the same function, but same period, so a smaller period. And I want to revolve this thing around here. So the area between these two curves, we want to revolve around here. Now when we revolve it from the outside, it's just going to look like the 7 times the sine of x over 3, because we'll see the outer part, but then you can think it's kind of hollowed out. So we can revolve this. As we pause it, we can kind of see that it's coming around, and it's only this moon-looking section as it goes around. And then we'll finish up, and so we have this shape, but it's hollowed out in the middle. And so how would we find the volume of that? Well, what we could do is we could find the volume of the outer one, and then we could find the volume of the smaller one and subtract them. And that's exactly what we'll do. So here are the two functions we just talked about. This was y equals 7 times the sine of 3 over x over 3. That was the higher function. And then the other one was y equals 5 times the sine of x over 3, which again gave us a period of 6 pi. So we looked from 0 to 3 pi. So this is 3 pi right here. And then we revolve this around the axis. And so we noticed we revolved it around, and we had this solid of revolution, but with the inside was cut out. So there's a little bit of a partway revolved shape. You have the green part, and then the blue part would have been cut out. And so here is the complete shape that we had. Now, if we think through this, to find the volume of of the the part between the two curves, what we could do is we could take the volume of the green one, the outer one, which we could go from 0 to 3 pi, or that 9.42 that we used, pi, times our function, or our radius squared. So the green one would have been this upper one, which was 7, times the sine of x over 3, dx. So we could have found that volume. And then we could have found the volume of the other one, and that would have been same idea, but from 0 to 3 pi. I forgot something up here. I forgot a squared. Squared. So we got pi times 5 sine of x over 3 squared dx. And that would have, so this would have been giving me the volume of the larger solid. So let's put a capital V, or volume of L, the larger solid, and this would have given me the volume of the smaller solid. So let's go V sub S. So what would the volume be if we just wanted the volume of this shape in here that would have been revolved around the x-axis? Well, you could have taken, so the volume that we want, we'll just put that in black, the volume that we want would have equaled, we can put a total maybe here, total volume would be the larger volume minus the smaller volume. And that's how we would do that. What we've learned about integrals, though, so this is nice. I know this is taking a while to write out, but we could have done this thing minus this one. Well, when we subtract two integrals, you can actually, as long as they're going from 0 to 3 pi, that both of them are doing the same thing, it's the same interval, we could have done just all of this together. So pi times 7 sine of 3 over x, x over 3, squared minus pi times 5 times the sine of x over 3 squared. And this whole thing dx. And so when we do solids of revolution, we can use this washers method. And the reasons it's called the washers method, I have one more thing which I didn't show you earlier. That so here I just went like for a small section, maybe from 4.5 to 5, and showed both curves rotating around. So you see how we have a washer here, this cutout shape. So what we're doing is we're kind of summing up the volume of all these different washers. We take the outer circle minus the inner circle, I should say the outer cylinder minus the inner cylinder. So you take out that hole in the middle, and that gives you the volume of that. So what we can notice is, we'll jump to this next slide. When we do this, and let's look at this bottom one first because it's wrapped around the x-axis, we can do the volume is going to be pi capital R, that means the larger radius, squared minus pi r squared dx. And then looking at this top one, this would be if our curve is rotated about the y-axis. You take the outer radius, the larger radius here, which in this case would be this one, and which is just our x squared, and you would subtract this one. So pi larger radius minus the pi times the smaller radius squared, dy, because it's in terms of y. And in this case, this would be from 0 to 4 because you do y values. So we have this new idea for volume. If you have the area between two curves that you're revolving around an axis. So let's take a look at an example here. Find the volume of the solid formed by revolving the region shown about the y-axis. So this is about the y-axis. So our volume is going to be equal to the integral. This is wrapped around the y-axis here. So we want to do things in terms of y. So here we're going from 0 to 4 pi. So we're going to do our larger radius squared minus pi times the smaller radius squared. The larger radius is this outer one. So that comes from y equals x squared, but we're rotating it around about the y-axis. So y equals x squared, which is our going to be our capital R. We actually have to solve for x, so we take the square root of both sides, and we get x is the square root of y. So that's going to be a larger radius. So the square root of y squared. And we're going to subtract pi times our smaller radius, which is g of x. And when we solve this one, so this one is y equals 2x squared. We want to solve for x, so we take half of both sides. So 1/2 y equals x squared. So x equals the square root. Taking the square root of both sides, we get 1/2 y, the square root of 1/2 y. So we're going to take our smaller radius, so this is our lowercase r, and we do 1/2, so square root of 1/2 y, and we square that. And this is going to be dy. So this simplifies a bit. The volume equals our integral from 0 to 4. We actually have a pi in both terms here, so we can factor out a pi. It can come outside our integral. The square root of y squared is just y minus 1/2 y. Well, that's even simple because those are like terms, so we have y minus half y, which is 1/2 y. Subtract those and you get 1/2 y. This is a constant, so we can actually bring that half out. So we have pi over 2 times the integral from 0 to 4 of y dy. And from there we can integrate. So we get a volume of 4 pi units cubed. Next one we're looking at here, find the volume of a solid formed by revolving about the y-axis. So around the y-axis again, the region bounded by y equals x equals 4, and the x-axis. So what you want to do is you want to usually sketch the graph so you can visually see what's going on. So these are all pretty easy to do. We have y equals x, and then x equals 4, which is a vertical line, and then the x-axis. So sometimes I'll draw out the graph, but this one's pretty simple to think through. So we have this graph here, and what we're going to do is we're going to revolve this around the y-axis. So it's going to go around the y-axis, and so when we do that, we get a shape that looks like this. So it's nice to visualize it. You don't always have to do that, but there you have it. So let's take a look at this. We're revolving around the y-axis. So we want to do our larger radius, which is all the way out to here, and subtract our smaller radius, which is to here. So the volume is going to equal the integral. This is in terms of y, so we're going to go from 0 to 4. Because these two intersect at 4. This was x equals 4 and y equals x, so our y value is 4. And then we're going to do our larger radius squared, and so pi, let's write out this pi capital R squared minus pi lowercase r squared. And remember this, it's revolving around the y-axis, so this is dy. Now let's plug in what we know. I already put the 0 and 4 there. Our larger radius is, now actually there's a pi in common, so let's go ahead and factor that out while we're at it. Our larger radius is this one, so it's just this length. This radius is always the same, it's a 4. So x equals 4, so 4 squared. And then minus, we factor out the pi, so the inner radius, well, that's this value here. We want it in terms of y. So x is equal to y, so that's y squared, and then dy. And we can integrate that. So the volume equals 128 pi over 3 units cubed. Our next one, find the volume of the solid formed by revolving the region shown about the x-axis. So right away we know this is about the x-axis. And when we go about the x-axis, we want to find the volume. The volume is going to be the integral in terms of x, so we'll just put from a to b right now, of pi times the larger radius squared minus pi times the smaller radius squared. And since we're going around the x-axis, this is dx. So we want to make sure we have x's in here and our indices here are in terms of x. So let's take a look. Well, we can figure out our index here. We are going x-axis, so from 0 to 1, it tells us this point is 1, 1. We're concerned about the x value. So we're going from 0 to 1. Pi times the outer radius squared. So it's going around the x-axis. So this function here is our outer radius, and that is y equals the square root of x. That's actually the form we want it in. So the square root of x is our larger radius, and then the largest radius gets squared. So larger radius squared minus pi times the smaller radius squared, which is this function here, and this function is x squared. So pi times x squared, that's our smaller radius, squared. Those are ones you got to be careful with because you write squared, but that's the function, so the function is squared, and then dx. From here, we can simplify this integral and then find the integral. So here we go. So the volume is 3 pi over 10 units cubed. Coming to our last one, the region between the graphs y equals x squared plus 2 and y equals 1/2 x plus 1 on the interval 0 to 1 is revolved about the x-axis. So our x-axis, find the volume of the solid of revolution generated. So it does help to sketch a graph, and we need to make sure we know how to do this. So y equals x squared plus 2, we know that's a parabola. shifted up 2 units. So we got a couple points here. So this looks like this. And then y equals 1/2 x plus 1. That is a line. Y-intercept of 1. Slope is 2. So up 1, right 2, down 1, left 2. Should be enough to get us a decent sketch of that. And we are looking for the interval between 0 and 1. So we're actually just looking at this small interval here between 0 and 1. And this is being revolved. Again, I highlighted it, but it's being revolved around the x-axis. So we have a very rough sketch of our two graphs, but it should be enough for us. So we know we want volume is going to be the integral from a to b of pi times the larger radius squared minus pi times the smaller radius squared. And this is wrapped around the x-axis, so we will put dx. And let's see what we have here. We can factor out this pi, which we've been doing. Integral, this is dx, so we want our x values. We know we want it on the interval from 0 to 1. It tells us there. Sometimes the two graphs intersect and you have to find their intersection, but not in this case. The larger radius is the one that's all the way up to here. So that's our parabola. So that's our larger radius. So we're going to use our parabola. We need to have it in terms of x because this is a y value. It's how high it is vertically. So it's a y value. So y equals x squared plus 2. So we want x squared plus 2, that's our larger radius, squared, minus, we factor out the pi, so we can put our smaller radius there. Our smaller radius has to do with the line. Again, it's how high it is vertically, which is a y value. Y is 1/2 x plus 1. 1/2 x plus 1 squared, that's our smaller radius, dx. So there is the integral that we want to evaluate, and we can go ahead and work through this. So our answer is 79 pi over 20 units cubed.